Okay, the next section of constant acceleration starts by talking about what are called SUVAT equations. Okay, a SUVAT equation we're going to have a look at a little bit later. I believe it is in the chapter, or it might even be the end of the book. These things are derived, so it's a set of equations that are derived from what we've been doing before. And what we did before is we did velocity time graphs. We also did displacement time graphs, but it's the velocity time graphs, these things in particular, that can be used to derive what we call SUVAT equations. And you're going to be working with these a lot. So let's move on from the start. Let's have a look here. So this graph here, this velocity time graph, can be used to derive a set of equations. Let's have a look at what these letters are. So S usually refers to displacement in mechanics. We're going to call our initial velocity U. So that's sort of like your starting velocity. Initial really means starting, or it also sort of, another way you can think of it is at t equals 0. Final velocity, this is the velocity at the end of the journey, or to be more accurate, really, it's like just before the end of the journey. And you'll see why I'm saying that a little bit later. A is our acceleration. Remember, the chapter is called constant acceleration. So acceleration is going to have a number that we are given or that we work out that stays the same throughout a question or part of a question. And t is used for time. So SUVAT is what we say. And with this velocity time graph here, we can use some of the stuff that we were doing in the last lesson to come up with these. So, for example, if we look at the gradient of the graph, you might remember that the gradient of the graph actually showed acceleration. So if you got the gradient of this, that would be the same as the acceleration. Well, what is the gradient? Well, it's the difference in y's, which is v minus u, divided by the difference in x, which is t in this case. So that's our first SUVAT equation. It can be used in this form, but it's normally written like this. So it reads like this. The final speed is the same as the final velocity is the same as the initial velocity plus acceleration acting for a given time. That's the way I like to think of that. So using the gradient derives this one here. What about area? So we know that area gives us distance, or it also gives us displacement if it's in one direction. So the area underneath, well, if we use the trapezium rule, so if we call this here u, and then if we call this one here v, the trapezium rule a plus b over 2 times height, well, my a is u, my b is v, and my height is actually sort of, it's turned. My height would be t. So you can end up getting this one here for the area under the graph. So these are our first two SUVAT equations. And you'll notice that they have 4 pieces of information. And this one here again, 4 pieces of information. So what's going to happen is I'm going to tell you 3 pieces of information, and you're going to tell me the 4th piece of information. That's how the most basic SUVAT equation question might work, without us needing to draw the graph anymore. So let's do an example. A cyclist is traveling along a straight road. Always try and draw and just think about the situation. We've talked about direction changing being important and so on. So you should always have some sort of basic idea of the context, what's going on. So along a straight road, she accelerates at a constant rate. So that, later on when you learn more mechanics, that's a really important phrase because it tells me that I can use SUVAT equations. So the acceleration is a constant rate from a velocity of 4. So that sounds like where we're starting. We're starting at 4. I'm going to call that u, to a velocity of 7.5. That sounds like v. In 40 seconds. Well, that sounds like a t value. So we're looking at a and u and v and t. And the way I would normally answer this question is I write down SUVAT. I think about what is involved in the question. So 4 is given to me, so I'll write that down. 7.5 is given to me. There's no idea of directions changing or anything like that, so I just write those numbers down. T is 40. Acceleration is not known. It's just known that it is constant. Find the distance. Okay, so I would do something like this. So I've got 1, 2, 3, 4. I'm thinking, what equation links those 4 pieces of information? Well, it was this one here. Okay, so if I put the numbers in here, I get my value for S. It's a bit like you're doing the trapezium rule without drawing the trapezium. Yeah, there's no need for you to do that. So you can use the SUVAT equations much, much faster. And they come from the graph anyway. So her acceleration in these 40 seconds. Now, one of the themes for harder questions is very important. So when you move between part A and part B, you need to ask yourself which numbers are the same and which numbers are different, because not everything is the same as you move throughout the question. As things change, the values that you need to use might change as well. So her acceleration in these 40 seconds, well, that one there is definitely the same. Are we still talking about this journey from 4 to 7.5? Well, the journey definitely starts at 4. You can't change that. If you started at 4, you started at 4. So that's definitely the same. What about the 7.5? Well, she's traveling at 7.5 when it's 40 seconds. And because we have 40 seconds again, it will be the same speed. So actually, that will be the same. But you see here, I can't just assume straight away that it will be the same. I need to think about if things are staying the same or if they're going to be different. Now, I'm not interested in distance anymore, so I'm going to get rid of that one there. What's her acceleration? So I'm looking now at a formula that links u, v, a, and t. Well, we saw on the last slide this one here. So putting the numbers in, rearranging, we can solve for a. Okay. Double check the answer. Does it make sense? Well, she's kind of going in one direction here, and then later on, she's still going in that direction, but she's going faster. So she must have accelerated. There must be acceleration. So yes, that makes sense. There is an acceleration, a constant acceleration throughout the question. A couple more examples. So a particle moves in a straight line from A to B. So A to B. It moves with a constant deceleration. Aha. So that's kind of like a negative because it means you're slowing down. Deceleration 1.5. So already I'm a little bit sort of cramped for space here, but I'm thinking this is a value to write down, minus 1.5. The reason why it's minus is it's a deceleration. We're moving, we can think of moving to the right, but our acceleration is sort of wants us to start going the other way. So it's acting against it, it's fighting the direction. That's why it has to be a minus. The velocity of the particle at A, well, A is the start of the journey, isn't it? So that must be u. Is 8, and the velocity at B, so B is the end of the journey, is 2. Let's just think about that. It starts at 8, it has deceleration, so it slows down. So it was going at 8, but then it's later only going at 2. Makes sense. Find the time taken from A to B. Well, all of this stuff here, this is about the journey of A to B. So I want to use these numbers here. Time times the thing I'm trying to work out. Okay, so V equals U plus AT for the first one. T equals 4 seconds. Then we have the distance from A to B. So when we're traveling just in one direction, A to B, we can sort of interchange the terms distance and displacement here. I had U and V and A, and it's the same journey, so I'm still going to use those. I could use T now, but I worked T out and T might be wrong. So let's not use that one. Let's say now I'm going to use UV and A, and I want to know S. So I'm looking for a formula that links S, U, V, and A. Well, it's that trapezium one again. We put the numbers in. Well, the trapezium one will require T, won't it? I suppose you will see later. There is a way that there is another formula we can use, but actually we haven't learned that yet. So no, sorry. In this case, we would need to use T equals 4 seconds. Later on, we won't need to do that, and you will see why. There's a different formula that we can use. Okay, that's the first part done. After reaching B, the particle continues to move. Right, so it sounds to me now like we have a different question. Okay, something different's going on. So I need to think about this carefully. I went from A to B. After reaching B, the particle continues to move along the straight line. So it's traveling at 2 meters per second here. So it's still going to carry on a little bit. The constant deceleration, look, they've given us that number again. So that's the same number. Okay, let's make a little bit of space here. So SUVAT, whoops, SUVAT. And I feel like I can put down that minus 1.5. What else? Not sure yet at this point. The particle is at the point C. Okay, let's pretend that's over here. 6 seconds after passing through point A. So the journey from A to C is 6 seconds. Okay, maybe I can use that number there. Find the velocity of the particle at C. Right. So C is, what is it? It's sort of like the end of the journey. So we're looking for velocity at the end. In other words, I'm looking for V. Now, S or U, I need another piece of information here. So could I use the 20 from before? No. The reason why I cannot use that is that 20 describes the journey from A to B. And what we're talking about here, the 6 seconds, we're actually talking about the journey from A to C. So that's not necessarily going to be 20. So we don't want to use that one. Well, what about U? Can we use the same U from the part of the question from before? That was 8. The velocity of the particle at A is 8. Well, if I talk about A to B and A to C, does the starting velocity change? No. It's just 8. And this is something that you're going to see as a consistent theme. U and also A generally stay the same when you move from one part of a question to another part of a question. Whereas the S and the V and the T are all sort of interconnected. If you go a different distance, you'll have a different speed and a different time and so on. So when you change the situation, when you change S, V, or T, the other parts of that also tend to change. Whereas U and A normally, I say normally, 95%, normally sort of stays the same throughout a question. Okay. So we've got 1, 2, 3, and V is unknown. So this looks to me like V equals U plus AT. Okay. And we actually get a negative answer. So don't be put off by that. Velocity is allowed to be negative. It means, well, what does it mean? It means you're going from A to B and then C. C is actually on the return part of the journey. So it changes direction. Now, does that make sense? Well, yes, it does. If something's always decelerating, it doesn't just mean that eventually it will stop. It means that eventually it will stop and then it will start to go the other way. In fact, it will even start to speed up the other way. Okay, so you are allowed negative answers for velocity and displacement, remember. Okay, the distance from A to C, well, you know, we can reuse these numbers. Okay, what have they gone for here? So they've gone for the one without A. Okay, so they've linked these numbers together, so you can find out the last one there. The key part I'd like you to take away from this is when you start changing the situation, you need to think carefully and even draw, I would say, what's happening. And that can help you make sense of what's going on. The other big theme that you will see throughout mechanics is U and A are often fixed because it's constant acceleration. In other words, it doesn't change. And U is the initial. And no matter how long you make the journey, the initial part is normally going to stay the same. Whereas the S, V, and T, when you change one of those, it will change the other parts. So that's what I would like you to take away from that. So pause this video here. Have a go at this question. It does also say about making sure that things are in SI units here, which is it's not the most common question in the world, but you will need to change this one to meters per second. Okay, have a go with that. If you're really unsure about the SI units, what I'd like you to do is to try the question just with kilometers per hour instead. Okay, and then I'll quickly talk about the changing of the SI units afterwards. So pause the video here and have a quick go. Okay, so I'm assuming you've done that. Let's take a look and talk through. So what have we got here? So traffic light along a straight road. So start drawing the situation. The car starts from rest. So when you're doing your SUVAT, starts from rest is a key phrase. You're going to see starts from rest an awful lot. It means the starting speed is 0, as they put here. Okay. So it starts from rest at the traffic lights, and 30 seconds later, it passes a speed trap. So I'm going to say that this is the speed trap. So this is that distance there is 30 seconds. Okay, so t equals 30. And it's registered as having this speed here. So we had our speed at the start, our speed at the end. So this must be v. Okay, now obviously they haven't chosen 45, they've done 12.5. The reason for that is up here, they've converted it to SI units. So we have 45. We need to change to meters per second. Well, the times 1,000, that's because you're changing from kilometers to meters. Now, when you get that answer, so let's write this out. 45,000 meters. Before I do this denominator here, that's how far you're traveling in 1 hour. But we want meters per second. So if you go from hours to seconds, well, an hour is an awful lot bigger. So you're going to need to divide. You need to divide by 60 and 60 again. You're dividing by like 60 squared. So that's why we divide this number. Think of it like direct proportion. When you multiply one side, you multiply the other. That's what's going on. So they get their 12.5. 1, 2, 3. 3 pieces of information. We're in a position now to find out the fourth. So they want the acceleration. Okay, I wouldn't even draw that one there. I've got u, v, t, a. So here's my formula. The numbers are in, and we get our answer. Okay. The distance between the traffic lights and the speed trap is the same journey. It's the same journey, isn't it? So we know that the initial speed will be the same. Acceleration, we could use that because it will be the same acceleration. The final speed is the same because it's the same journey. The time is the same. So use any 3 pieces of information from before with the formula, and they will give you that answer there. Okay. So start having a go there then at exercise 9C, and we'll talk about some more complicated SUVAT in the next lesson.